Hey guys, this video is on lattice enthalpy, bond energy, and the Born-Haber cycle. So let's look at sodium chloride. We know that the first ionization energy for sodium, which is described by this process right here, is positive 496 kilojoules. And we also know that the first electron affinity for chlorine, which is described by this equation here, is negative 349 kilojoules. Now if we just add up these two equations, it looks like we're forming sodium chloride from its constituent elements. But when we add up the changes in enthalpy, we get a positive number. And that definitely can't be right, because we know that whenever we form an ionic compound from its constituent elements, we release energy. It's an exothermic process. Delta H is negative. Something must be missing. What could it be? It's lattice enthalpy. Lattice enthalpy is the enthalpy change associated with combining separate gaseous ions into a solid ionic compound. That is described for sodium chloride by this equation right here. Taking the gaseous ions, the sodium ion and the chloride ion in the gaseous state, letting them combine and form solid sodium chloride. The change in enthalpy associated with this process is the lattice enthalpy for sodium chloride, and it ends up, for sodium chloride, it's negative 788 kilojoules. Now, a couple things about lattice enthalpy, guys. First is, I'd say about half of the textbooks that you see define it the opposite way. The amount of energy required to break apart the solid ionic compound into its constituent ions in the gaseous state. And when they do that, their lattice enthalpies are positive. The same number, but positive. I believe the textbook, the OpenStax textbook, does it that way, but we're going to do it this way. To me, this makes a little bit more sense. So we're going to define it just how I did up here. Now, so once we add the lattice enthalpy into the process, then now we get the right answer. Now, the lattice enthalpy can be calculated, that's down here, using Coulomb's law. And it ends up that the lattice enthalpy is proportional to the charge on the two ions divided by the distance between them after they form the ionic compound. Now, the distance between them we can usually approximate pretty well as the sum of the ionic radii, the radius of the cation plus the radius of the anion. It works pretty well. And so we can see from looking at the lattice enthalpy, the Coulomb's law basically here, that the greater the size of the charges, and in this equation here, by the way, if you choose the constant of proportionality carefully, then you can use just the integral charges, plus 1, minus 1, plus 2, minus 2, etc., which is what we do. So the greater the size of the charges, the greater the lattice enthalpy, the more negative it is. That's what we say. Also, the smaller the distance between those two ions when it forms that ionic compound, the greater the lattice enthalpy. A lot of times, I think it's easier to look at the force of interaction between the two particles. You get the same thing. It ends up that if you calculate the force from the energy, it's basically just proportional to, same thing, Q1, Q2 over the distance squared. You get the same behavior. You can explain it using either equation. So what that boils down to is this right up here. The greater the charge and the smaller the ions, the greater the lattice enthalpy or energy, same thing. So if we look at these examples here, if you look at this top row here, what's consistent between these three compounds is that, first of all, the anion is always iodide, so that size stays the same. The charges are all plus 1 and minus 1, so the Q's stay the same all the way across. What's changing is the D. So these are the sum of the ionic radii, and we get the lithium being the smallest of these three ions, lithium, sodium, potassium. This distance is the smallest, so we get the most negative force, and we get the largest lattice enthalpy or energy of these three. And potassium being the largest gives us the largest D, and so that means we get the smallest lattice enthalpy. Coming down here in this row, what's changing is the charge. If you look at the sum of the ionic radii, they're really pretty similar. They're not significantly different. But we go from plus 1, minus 1 to plus 2, minus 2 to plus 3, minus 3. And so the larger charge gives us a larger lattice enthalpy, and the smaller charge gives us a smaller lattice enthalpy. Now, what if these two things are going in opposite directions? What, for example, let's say if the distance between the two ions is getting smaller, but the charges are getting smaller. It ends up that the charges have a much larger effect on the lattice enthalpy than the distance between the two ions. So if those two are going in opposite directions, then, because remember, smaller distance increases the lattice enthalpy, larger charge increases the lattice enthalpy. If they're going in opposite directions, the charge almost always wins out. So with that in mind, let's do this example. For each of the following pairs of compounds, so we're going to compare gallium nitride to magnesium oxide, which one has the largest, meaning the most negative lattice enthalpy. And then we'll compare rubidium iodide to sodium fluoride and strontium telluride to potassium oxide. These are some of the ionic radii if you want, but you can actually figure this out without these numbers, but I just threw it up there for you. Nitride's not there, it would be right here. So why don't you guys figure this out for yourself, pause the video, and then when you get an answer, come on back. Welcome back. Actually, we still need to answer it. So between these two, the distance between gallium nitride and magnesium oxide is roughly the same. Magnesium 65, these are picometers. Oxide is 140, so it's about 205. Gallium nitride, gallium 62, nitrides, going to be a little bit larger than 140, but it's going to be about the same, about 200 something. So that's not the factor, it's the charge. So 3 beats 2, or negative 3 times positive 3 is negative 9, beats negative 2 times positive 2, which is negative 4. So gallium nitride, between these two, would have the largest, most negative lattice enthalpy. Now comparing rubidium iodide and sodium fluoride, these are both plus ones. Rubidium's plus 1, sodium's plus 1, iodide's minus 1, fluoride's minus 1. So the charges, the product of the charges is the same for both of these guys. Now it's the distance between them that matters. Rubidium and iodide are both larger than sodium and fluoride, and so that means that rubidium iodide will have a smaller, less negative lattice enthalpy. Sodium fluoride will have the larger lattice enthalpy of these two. Going down to strontium telluride and potassium oxide. Now here, strontium telluride, we have plus 2 and minus 2, and when you add up these radii, we get about 334. For potassium oxide, we get plus 1 and minus 2. So this product of the charges is smaller. The sum of the radii is like 273, so it's smaller. So there's an instance where the distance is getting smaller, so that would tend to increase the lattice enthalpy, but the charges are smaller. One of them is anyway, so that would decrease the lattice enthalpy. Well, as I said, the charge, the difference in charge is a much stronger effect than the difference in the distance between them. So what we can say is that the rubidium telluride is going to have the largest lattice enthalpy between these two, because plus 2 times minus 2 beats plus 1 times minus 2. All right. Now, bond energies. The bond energy, also bond enthalpy, it's the enthalpy change when a bond is broken. So, for example, in the nitrogen molecule, it ends up there's a triple bond between the two nitrogen atoms in nitrogen. If the amount of energy it takes to break this bond and form two separate nitrogen atoms is the bond energy for that bond, it ends up, for that bond, it's positive, it's 946 kilojoules. Bond energies are always positive, guys, because you always have to put energy in to break a bond. Going in the opposite direction, forming a bond from the atoms is always a negative. Delta H is always negative. It's an exothermic process. Energy is always released. Same amount. If we were to take two nitrogen atoms and form a nitrogen molecule with a triple bond, delta H for that process would be negative 946 kilojoules. Now, the higher the bond energy, the stronger the bond. Stronger means harder to break. The stronger a bond is, the shorter it is. As long as the two atoms on each side are, we're comparing apples to apples, same two atoms. So here's a table of bond energies. This is probably the one I'll give you guys on the exam to use. It's not comprehensive, but it has as much as we'll need. So we can use average bond energies to calculate approximate energy changes for chemical reactions. And so so this word right here, average. This table here, these are average bond energies. I say average because the actual energy for a bond between two atoms is going to depend upon its environment. What other atoms are around it? Is it in a solid, liquid, or gas phase? What other atoms are affecting it, right? So we take an average and it gives us a pretty good idea. But we can use these numbers to approximate delta H for a chemical reaction. And to do that, so what's going on here, is we are using the property of enthalpy and change in enthalpy, that it is a state function. We talked about this back in the thermochemistry module. Remember, a state function means that its value only depends upon where it is and not how it got there. And so what we're doing here, is we're making up an entirely imaginary process, guys, but one in which we can look up the change in enthalpy for every step. So what we're saying is the change in energy or enthalpy for a reaction is going to be approximately the sum of the energy that it takes to break apart all the bonds in the reactants. So the sum of the bond energies of all the reactants minus the bond energies of the products. So the idea here is we're imagining, and again, this is not how it happens, guys, but because enthalpy is a state function, which is really cool, we can do this. So we can say we're imagining that we're taking all of the bonds in all the reactants and breaking them. And we can look up the amount of enthalpy it takes to do that because we can look up bond enthalpies, bond energies. And then we're imagining we're reforming those bonds to make the products. And when we do that, we release energies. So that's why it's a negative, because it's the negative of the bond energies of the bonds. And so we can use, this is another application actually of Hess's law, again, thermochemistry module. So let's use an example to illustrate how this works. So we want to approximate the energy of reaction for the following reaction. So the combustion of methane, CH4 plus oxygen goes to carbon dioxide plus 2 waters. So use these numbers over here, guys, and see if you can come up with an answer. So pause the video, work it out. When you're finished, come on back. Welcome back. So what we do is we just look up the bond enthalpies for all the bonds in the reactants. So methane has 4 carbon-hydrogen bonds. So we look up carbon-hydrogen, it's 415. 4 times 415 kilojoules. Plus, there are 2 oxygen molecules. That we have to take that 2 into account right here. Each oxygen molecule has 1 oxygen-oxygen double bond, and that's 498 kilojoules. So those are the bond energies of the reactants. What we're doing is we're imagining we're breaking apart all the bonds in the reactants, and it takes this much energy to do that. Then we're going to reform those bonds to make the products. And so we look up the carbon-oxygen double bond, which is right here. And because there's 2 carbon-oxygen double bonds in carbon dioxide, we multiply that by 2. And then we form the oxygen-hydrogen bonds in water. So we look up oxygen-hydrogen single bond energy, 464. There's 2 water molecules. Each water molecule has 2 oxygen-hydrogen bonds. That's why we have to multiply the bond energy of the oxygen-hydrogen bond, by 4. So we subtracted everything over here. So the left set of brackets is the amount of energy it takes to break apart all the bonds in the reactants. The right bracket is the amount of energy that's released when we reform all of the bonds in the products. When we add these numbers up, we end up getting negative 680 kilojoules, which is reasonable. It's a combustion reaction. We expect that we're going to release decent amount of energy. Next, the Born-Haber cycle. So once more, guys, we're going to use that wonderful property of enthalpy, that it is a state function. And we're going to come up with another imaginary process that lets us calculate properties that we otherwise could not. And that is the lattice enthalpy. The lattice enthalpy, by the way, is not something that we can measure directly in the lab. There's no way to actually do that experiment. But we can use the Born-Haber cycle. So the Born-Haber cycle Let's look at this example over here. The idea is this: you imagine we're using lithium fluoride here, so solid ionic lithium fluoride. We break apart that lithium fluoride into its constituent elements. Remember, these are imaginary processes that we can look up the enthalpy change for. And so the breaking apart lithium fluoride into its constituent elements, solid lithium, that's the elemental form of lithium, and fluorine gas, which is the elemental form of fluorine. And we balance it because there's one fluorine atom here, we have to put a 1/2 here. So again, we're breaking the compound up into its elements in their elemental forms. So we can look up that energy change. The opposite, forming lithium fluoride from its constituent elements, that's the definition, if you remember back to the thermochemistry module, of heat of formation. So we can look up the heat of formation of lithium fluoride, and the amount of energy it takes to break that apart is negative of that. So the enthalpy change associated with this is step 1, be negative of the heat of formation. Next step, we always follow the same steps in the Born-Haber cycle, is to make everything into a gas. In this case, fluorine's already a gas, so we don't have to worry about that. If it were a liquid, then we'd have to, like say bromine, we'd have to make it into a gas. Now lithium's a solid, so we do have to make it into a gas. That enthalpy change is either the heat of vaporization, if it's liquid to a gas, or heat of sublimation, as in this case it's a solid to a gas. So we can look that number up. So we have the enthalpy change for this step, and that's always the second step. Third step is form the cation. So the cation is going to be the metal ion. So we pull that electron or electrons off of that metal to form the gaseous cation. That is the ionization energy. Now make a note of this, guys, write this down. If it ends up being a +2 cation, you have to add together the first and the second ionization energies. If it's a +3 cation, you have to add together the first ionization energy, second ionization energy, and third ionization energies for this step. In this case, it's just the +1, so we just need the first ionization energy. Next, any bonds that are there, we break. In this case, a fluorine molecule has a bond, a fluorine-fluorine single bond. We have to break that bond. Now, because there's a 1/2 here, we're going to end up multiplying that number by 1/2. But that's a number we can look up. We just talked about that. That's bond energy. So we can look up that number. Next, we take that, we form the anion from the nonmetal. So we're going to form the fluoride ion from the fluorine atom by adding an electron. We have a name for that process too. That's electron affinity. So we can look that number up. Now, again, write this down, guys. If you form a -2 cation, you have to add together the first electron affinity and second electron affinity. You can look these up. If it's a -3 cation, you have to add together the first electron affinity, the second electron affinity, and the third electron affinity for this steps, our step 5. And then finally, in step 6, we combine the gaseous ions to form the solid ionic compound. That's the lattice enthalpy. So because this is a cycle, guys, this is a circle. It's because we end up at the same place that we start, the total sum of all the enthalpies must be equal to 0 because enthalpy is a state function. See how beautiful that is? All right, so what we do, the way we use the Born-Haber cycle, is usually it's to find the lattice enthalpy, but we could actually find any of these properties in here. As long as we know the other 5, we can solve this equation right here. This is the equation we use right down here for the Born-Haber cycle. The sum of the enthalpy changes for every step must add up to be equal to 0. So let's say we want to find the lattice enthalpy. That would be our delta H6. Then we just bring everything else over to the other side, so delta H6 is equal to negative of the sum of all these. And we can look all these numbers up and get the answer. It's really not too bad. So let's do an example. We want to calculate the lattice enthalpy of lithium oxide now. And we're given this information. The heat of formation of lithium oxide, negative 595.8 kilojoules per mole. The heat of sublimation of lithium solid, the first ionization energy for lithium, the first and second electron affinities for oxygen, and the bond energy of an oxygen-oxygen double bond. That's all the information you need. So why don't you guys give this a shot? When you get an answer, come on back. Welcome back. Let's work it out. So this is the equation that we use. The sum of the changes in enthalpy is equal to 0. We'll call delta H6 our lattice enthalpy. That's what we're asked to find. So we rearrange it like this, and we were given all the other numbers. So the heat of formation of lithium oxide was negative 595.8 kilojoules. So because we're breaking it apart, it's the negative of that, so it becomes positive. Okay, make sure you catch that. That's why this is a positive number. And then the heat of sublimation, just that number right here. And then the ionization energy, where we're pulling that electron off of lithium, 520 kilojoules. And then next, what we do is we break the bond. So we have 1/2 of an oxygen molecule, because there's one oxygen in lithium oxide, right? So we have to, just like we did with the fluorine, right? So 1/2, it's not always 1/2, by the way, it's 1/2 because the elemental form for oxygen is O2, and we only have one oxygen in lithium oxide. So 1/2 times the bond energy for the oxygen-oxygen double bond. And then we add the 2 electrons. Now here, because we form the oxide ion, which has a -2 charge, we have to add together the first and the second electron affinities. And we do. And we add all that up, and we get our answer. It's negative 2,127 kilojoules per mole. That's all there is to that, guys.